Hello, this is not your chem tutor, and in this video, we will be talking about the ideal gas equation. Now, the ideal gas equation is something you will encounter in general chemistry, and if you are a chemistry major, you will encounter this again in the early portion of physical chemistry. Before you continue this video, I hope you have watched my other videos about the other ideal gas laws. So I made separate videos about Boyle's law, Charles' law, Guy-Lussac's law, Avogadro's law, and combined gas laws. If you haven't watched them yet, you can view them using the links I put on the description box. And in this video, as usual, in the end, I put examples, 3 examples, so we can practice some calculations. Now let's move right away to the ideal gas equation. So the formula is actually very simple. It's pretty straightforward. PV equals nRT. Now let's define each variable. P is pressure, V is volume, N is the number of moles of gas, R is the gas constant, and T, of course, is temperature. Now, if you have watched my other videos about the other ideal gas laws, you can see in their formulas that you have P1 and P2, V1 and V2, N1 and N2, T1 and T2. It's because those formulas, those ideal gas laws involve changes. So you have initial values and final values. However, in the ideal gas equation, in PV equals nRT, you only see one value for pressure, one value for volume, one value for the number of moles of gas, and one value for temperature. Therefore, this ideal gas equation is useful to answer problems that do not involve changes in pressure, volume, number of moles, and temperature. Okay? So that's the basic premise of the ideal gas equation. Now, at this point, I would like to emphasize that there are different values of R, or the gas constant, and they have different units as well. In this video, I will introduce you to two of the most commonly used value of R. The first one is 0.0821 liter atmosphere per mole Kelvin. And the second one would be 8.314 joules per mole Kelvin. Now, students usually ask, how do they know which value of R should be used in the problem? Now, the answer is, it depends upon convenience. Now, there are problems that it is more convenient to use the 0.0821. And there are other problems that it is more convenient to use the 8.314. So you should read the problem, look at the given, and decide on which value of R is more convenient to use. Now, I just want you to remember that if you are using this value of R, make sure that the pressure you are plugging is in ATM, or atmosphere. Make sure also that the volume you are putting into the formula is in liters. Make sure that the number of moles is in the unit moles. And make sure that the temperature is in Kelvin, or K. On the other hand, if you are using this value of R, make sure that your pressure is in Pascal Make sure that your volume is in cubic meters. Your N is in moles. And your temperature is in Kelvin. You should not interchange the units. The units must be strictly followed if you are using R equals 0.0821 or R equals 8.314. Otherwise, you will get an incorrect answer. Now, make sure also that you are familiar in converting pressures and converting temperatures. If you're still not familiar with converting units of pressure and temperature, I made separate videos and you can check those videos using the links I put on the description box. Now let's proceed to example 1. A sample of oxygen gas kept in a 3.4 liter container at 27 degrees Celsius exerts a pressure of 2.5 atm. Calculate the number of moles of oxygen gas present. So we will be using the ideal gas equation. So let us list the variables. The pressure given in the problem is 2.5 atm. The volume given is 3.4 liters. N is the number of moles which is missing in this problem. It's the one being asked. Calculate the number of moles of oxygen gas. So that's unknown, so just write question mark. Now 27 degrees Celsius is our temperature, but remember, we previously discussed that the temperature must be in Kelvin if you are solving ideal gas law problems. So to convert 27 degrees Celsius into Kelvin, what you need to do is you just add 273.15 to 27, and this is equal to 300.15 Kelvin. So this will be your temperature in Kelvin. And then for the value of R, you decide on which value of R is more convenient to use. If you look at the units, the pressure is atm, the volume is liters, so the more convenient value of R to use is the 0.0821 liter atmosphere per mole Kelvin. Actually, this is the more common value of R. It's more commonly used than the 8.314. So this is also what I use personally in most problems. Now let's substitute the values into the equation. So PV equals nRT, so we have P V equals N, which is unknown. So just write N, and then R, and then T, which is 300.15 Kelvin. So in order to solve for N, what you do is you divide both sides of the equation by 0.0821 liter atmosphere per mole Kelvin and 300.15 Kelvin. And you do the same thing on the other side. 0.0821 liter atmosphere per mole Kelvin times 300.15 Kelvin. So R will cancel on the right side as well as temperature. So what remains on the right side is N. And on the left side, you can see that the liters will cancel out, ATM will cancel out, and Kelvin will cancel out. So the remaining unit on the left side is moles, which is what we are looking for in this problem. So the unit would be moles. Now, if you solve this in your calculator, 2.5 times 3.4 divided by 0.0821 times 300.15, the answer is approximately equal to 0.345 moles. And this is the answer, final answer to the question. Now let's proceed to our second example. Calculate the pressure in ATM exerted by 1.03 moles of helium in a 4.50 liter steel vessel at 50 degrees Celsius. So again, we will use the ideal gas equation. So let's enumerate the values. P is missing in this problem. It's the one being asked. Calculate for the pressure. So it's unknown. The volume is 4.50 liters. N is the number of moles, which is 1.03 moles. T is the temperature, which is 50 degrees Celsius. But again, we will convert this into Kelvin by adding 273.15. So 50 plus 273.15, this is equal to 323.15 Kelvin. And then for R, we will be using 0.0821 liter atmosphere per mole Kelvin because our volume is in liters and the pressure being asked must be in ATM. So it's more convenient to use the 0.0821. Now let's substitute the numbers into the equation. So P is unknown, so just write P. The volume is 4.50 liters equal to N, 1.03 moles. R is 0.0821 liter atmosphere per mole Kelvin. And then T is the temperature, 323.15 Kelvin. Now to solve for pressure, what you can do is you divide both sides by 4.50 liters. So 4.50 cancels on the left side. So what remains on the left side is pressure. And on the right side, as you can see, liters will cancel, moles will cancel, and Kelvin will cancel. So what remains as the unit is ATM, which is the unit for pressure. And then we solve the right-hand side of the equation. 1.03 times 0.0821 times 323.15 divided by 4.50. This is equal to 6.07 ATM. This is the answer to the question. For the last example, at what temperature in degrees Celsius will 0.300 moles of nitrogen gas occupy 10.0 liters at 1,400 millimeters mercury? So again, same equation, ideal gas equation. The pressure given in this problem is 1,400 mmHg. Now, if we are going to use the 0.0821 as the value of R, we need to convert this into ATM or atmosphere. So as we have learned in my separate video, in order to convert mmHg into ATM, we know that 1 ATM is equivalent to 760 mmHg. So mmHg will cancel out, and then you have ATM left. So 1,400 times 1 divided by 760, that is equivalent to 1.842 ATM. So this is our pressure in ATM. The volume given in the problem is 10.0 liters. And then the value of N is 0.300 moles. Temperature is unknown in the problem. It's the one being asked. So what temperature? So just put question mark. And then the more convenient value of R to use is 0.0821 liter atmosphere per mole Kelvin. Now you might have already noticed that I'm biased in using this R. I prefer to really use the 0.0821 more than the 8.314. But it still depends on what is given in the problem. Okay, so let's substitute the values. Pressure is 1.842 times the volume is 10.0 equal to N 0.300 moles times R 0.0821 liter atmosphere per mole Kelvin times T, which is unknown, so just write T. To solve for T, you will divide both sides of the equation by 0.300 and 0.0821. Do the same thing on the left side. So 0.300 will cancel on the right side as well as the 0.0821. So what remains on the right side is temperature. And on the left side, as you can see, ATM will cancel, liters will cancel, and then moles will cancel. So the unit left on the left side is Kelvin, which is the unit for temperature. And if you solve this in your calculator, 1.842 times 10 divided by 0.3 times 0.0821, this is equal to 747.87 Kelvin. However, this is not yet the answer. If you read the problem, it says here at what temperature in degrees Celsius. So your answer must be in degrees Celsius. So in order to convert the temperature from Kelvin to degrees Celsius, what you need to do is you need to subtract 273.15. If you do that, 747.87 minus 273.15, that is equal to 474.72 degrees Celsius. And this is the answer to the question.